Hi everyone, I'm John Boprowski and welcome to my webinar on how to create perfect IBIS buffer models from circuit data. Please type any questions into chat as I proceed with this webinar. I'll have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? Well, high-speed digital integrated circuits and serializer-deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations. This webinar is to let you know about the process I've used for many years to create perfect IBIS buffer models from circuit data, and it's available to you for free. What is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I've learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit data and use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. I'm here to share my learnings over the past 10+ years and introduce you to the same IBIS buffer modeling I've used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce you to the process I use to create perfect IBIS buffer models for use in channel simulators. Perfect means that the IBIS buffer model exactly agrees with the SerDes circuit for the channel facing differential impedance. Perfect also means that use of this IBIS buffer in IBIS-AMI models results in exact agreement with the SerDes transmit or receive circuit LTI characteristics. Finally, I show you how you can get for free the tools I use to create perfect IBIS buffers and use them to create perfect circuit IBIS-AMI models. So let's talk about modeling SerDes system in the channel simulators. Channel simulators are based on the IBIS Open Forum standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. The block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: the transmit IBIS-AMI portions, where the AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's the transmit package, the channel, and the receive package. These pieces represent the differential channel. Each part is optional and may be represented using S parameter files. the receive IBIS-AMI portions, where the AMI portion typically contains a continuous time linear equalizer, a clock and data recovery unit, and a decision feedback equalizer. The IBIS portion has a differential input from the channel. A key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. Creating perfect IBIS-AMI models from circuit data. So, IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I have used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on circuit data they provided me. In today's webinar, I provide instructions on modeling, transmit, and receive IBIS buffer models from circuit data. The modeling data is collected typically from a SPICE circuit simulator. To start, let's talk about the typical SerDes system test points. This figure shows these typical test points. For the current discussion, TP0 and TP1 are used for the transmitter, and TP4 and TP5 are used for the receiver, the data collection points. TP0 is for the transmit LTI circuit input. TP1 is the transmit SerDes differential buffer output. TP4 is the receive SerDes differential buffer input, and TP5 is the receiver LTI circuit output. The transmit circuit IBIS buffer is per the IBIS specification, and the specification defines the IBIS buffer to be linear and time invariant. The top figure per the IBIS pre-IBIS 7.0 spec shows that the transmit IBIS buffer circuit representation per pin for the differential output and is defined in the IBIS file. The bottom figure, which is per the IBIS spec 7.0 and beyond, shows that the transmit IBIS buffer can be represented with 4-port S parameter data. When used, the IBIS buffer in the IBIS file is ignored. The receive circuit IBIS buffer is also per the IBIS specification, which defines the IBIS buffer again as linear and time invariant. The top figure, as before, per the pre-IBIS 7.0 spec shows that the receive IBIS buffer circuit representation per pin for the differential output and is defined in the IBIS file. The bottom figure, per the IBIS spec 7.0 and beyond, shows that the receiver IBIS buffer can be represented with 4-port S parameter data, and when used, the IBIS buffer in the IBIS file is ignored. The S4P file for an IBIS buffer is defined in the IBIS-AMI file. These are the reserved parameter lines used for the transmit IBIS-AMI model and for the receiver IBIS-AMI model. Both sets define the S4P file and the termination resistance. The transmit lines also include the source peak-to-peak voltage swing. When the AMI file defines the S4P IBIS buffer, then any IBIS buffer defined in the IBIS file is ignored. The IBIS buffer using S4P data per the 7.0 and later specification has a number of pre-7.0 has a number of major limitations. There's no coupling between the plus and minus differential terminals. There's limited circuit characteristics for modeling. However, the 7.0 and beyond IBIS buffer representation using S4P data captures the full fidelity of a circuit's IBIS buffer and can be captured using SPICE circuit simulations. The S4P data is preferable for capturing the circuit's fidelity. However, problems are typically encountered when trying to obtain the S4P IBIS buffer representation from SPICE circuit simulations. For discussion, transmit SerDes circuit is assumed. To capture the transmit circuit IBIS S4P buffer characteristic, the transmit circuit needs to have a distinct point between the AMI and IBIS portions in the circuit where the IBIS and AMI portions can be modeled independently. In many transmit circuits, this point does not exist. Loading between the AMI and IBIS portions is typically not a simple resistance, and reflections typically occur. For these cases, the only IBIS characteristic readily accessible is the impedance into the differential channel, which can be measured with S2P data, and that S2P data can then be converted to S4P data. So, let's talk about converting S2P data to S4P data. And these figures show the typical conversion. They set the start, stop, and step frequencies to be the same as for the S2P file. For the transmitter, within the AMI file, set the transmit resistance equal to 50 ohms and the transmit voltage, peak-to-peak swing, to 1000. And for the receiver, within the AMI file, set the receiver resistance to high impedance. Here I list 1 e to the 9. So when modeling an AMI, when using S4P data for the IBIS, the waveform data is collected from the transmit LTI input to the differential output for the transmitter, or differential input to the output for the receiver. The AMI model is created by de-embedding the IBIS S4P characteristic from the waveform data. This is done by representing the IBIS S4P characteristic with its impulse response. The inverse of the FFT of this impulse response is de-embedded in the time domain from the circuit waveform data. SerDesDesign.com provides IBIS de-embedding. It has many tools that automatically de-embed the IBIS buffer characteristic from the circuit response data. This includes the free web-based channel simulator and its downloadable Windows PC copy. Here are screen captures from the channel simulator parameters that enable IBIS buffer de-embedding. There's IBIS de-embedding tools that are available from SerDesDesign.com store. And all tools are available for free for 1 month for use on a Windows PC. The channel simulator tool is for a single channel system. It's the same as the free web-based tool. No internet connection is required. It uses your PC processors and your file directories. There is an IBIS-AMI model generation tool used to convert any included transmit and receive behavioral model to IBIS-AMI models. It's an add-on to the channel simulator tool, and it includes the SerDesDesign.com IBIS-AMI model development environment. Here's 2 additional tools. There's a transmit FFE modeling tool. It treats the SerDes FFE circuit as a black box. You collect the circuit waveform data and the differential output S2P data, and the tool automatically derives the IBIS and AMI portions of the IBIS-AMI model. The AMI model automatically extracts the FFE gains and filtering properties from the circuit data. And there's a transmit and receive CTLE modeling tool. Again, the CTLE circuit is treated as a black box. You collect the circuit waveform files and the differential transmit output or receiver input S2P data, and the tool automatically derives the IBIS-AMI portions of the IBIS-AMI model. So check these tools out. Check them out on my own dime. I personally guarantee that you will be successful using the Windows PC copy of my SerDes.com tools. You have a full 30 days to put it to the test. After that time, if you see the value in it, then you can buy it. I only want you as a customer if you're 100% happy with your investment. Simple as that. This webinar has shown you how to achieve perfect transmit and receive IBIS buffers for use in IBIS-AMI models, where perfect means that the IBIS buffer model exactly agrees with the SerDes circuit for its channel facing differential impedance, and perfect also means that use of the IBIS buffer in IBIS-AMI models gives exact agreement with the SerDes circuit linear and time invariant backend for the transmitter or front end for the receiver. This is achieved by modeling the IBIS buffer with S4P or S2P data. SerDes.com tools automatically convert the IBIS S2P or S4P data and automatically derives the IBIS and AMI portions of the IBIS-AMI model. So this ends this webinar presentation, and so I'll end the recording of this webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. Thank you.